Hi everyone, my name is Manolis Savva and I'm an assistant professor at Simon Fraser University. Thank you for watching this talk. The title for this talk is Frontiers for Holistic 3D Vision, Simulation for Embodied AI. It will be a high-level talk sketching out some upcoming research challenges, in my opinion, for research in holistic 3D vision. So let me first get started by describing what I mean with this part of the title here, saying simulation for embodied AI. So what really do I mean when I use these terms? There's different interpretations of how one might understand this term. So I first want to give you a little bit of a background of where this terminology is coming from. So concretely, this part of the terminology, this embodied AI, is coming from the so-called embodiment hypothesis, which is the idea that intelligence emerges when an agent can interact with an environment and when that agent can perform some sensory motor activity in that environment. This is a very interesting idea presented in this cognitive science paper here by Smith and Gasser on the development of embodied cognition in babies. And I highly recommend that you check this paper out if you're interested in some of this foundational work in cognitive science. So in other words, if we were to say what this embodiment hypothesis means is that the intelligence that, say, humans and other animals exhibit can only emerge because these humans and other animals in the real world are allowed to interact with the world. So that's the general idea of the term embodied AI. And when we talk about this embodied AI, we can interpret it as the goal, having the goal to develop artificial intelligence that exhibits similar kinds of intelligence as humans. What are some concrete examples of embodied agents in the real world? We can think of the example of robots, such as the one that you see here, participating in the DARPA challenge and attempting to open a door. So robots are, of course, physically embodied agents that are taking actions in the world. And in popular fiction and in science, in some sense, one of our long-term goals is to get robots and other such physically embodied agents to exhibit some level of human-like intelligence, human-like artificial intelligence. Usually what this implies is the ability to do some active perception in the world, to do long-term planning, to break down a large task into subtasks that can be carried out in sequence, and then to also learn how to carry out tasks by interacting with the real world. So these are, of course, challenging research problems. And what's interesting is that in recent years, we have seen a bit of a shift emerge in the computer vision community, part of the computer vision community, and also other related communities, from tasks and research problems that are primarily formulated on internet image data sets, such as, for example, ImageNet, some images from which you see on the left here. So these kinds of internet AI tasks that include things like doing object detection in internet images or human pose estimation and so forth, to tasks that are in this new realm of embodied AI. These tasks are tasks that have strong connections with robotics, for example, of getting a real robotic system to be able to navigate in the world, to perceive objects and interact with them, and also tasks that have to do with otherwise assisting people as they go about in their daily lives. Say, for example, in artificial intelligence assistants that are operating on some augmented reality glasses, where as you go about your daily life and you have meetings and so forth, they bring up relevant, contextually relevant information to you. They understand your context and they suggest information. They can answer questions and so forth. Both types of settings here are, I think, fall under this umbrella of embodied AI. Now, going back to the to that title in the beginning, the lower part of it was the simulation for embodied AI. And so what does simulation mean? Now that we've talked a little bit about the embodied AI part, simulation essentially means to take that statement about the physically embodied agent taking actions in the world, whether as a robot or as some software system that's in a system that's a person is wearing, say the augmented reality glasses, to take this and then to change it slightly into the setting of having a virtual version of this embodied agent taking actions in a virtual world. So this is the notion of simulation that I was implying as part of that title, to simulate these physically embodied agents in a virtual world. So that's that. Now that we've talked about the simulation part, why is it relevant? So along with the shift that I was describing earlier of going from this set of tasks focusing primarily on internet AI to embodied AI tasks, there's a corresponding transition of the needs of the community from relying primarily on static image datasets such as ImageNet, Pascal, MS Coco, VQA, and so forth, to now needing to rely on 3D simulators. In some sense, 3D simulators are becoming the new datasets in order to be able to carry out these kinds of embodied AI tasks, to develop methods, to benchmark them, and then to measure progress. One needs to be able to do simulation to allow this kind of active embodied system to take actions and then to measure its performance. And this is where simulation becomes relevant. So this has been a shift that has been occurring for a few years. And I want to go back to this roughly year 2017, a point in time at which I think there were quite a few exciting developments, and give you a sense of what the world looked like at the time from the perspective of people beginning to tackle these kinds of embodied AI research problems. So year 2017 was quite exciting. And one interesting thing that was happening at the time was the emergence almost at the same time of several 3D simulation software platforms, some examples of which you see here. There were actually, this is, by no means is it an exhaustive list. There were close to a dozen or so efforts within that year. And I'm only showing examples here for interiors. I'm not even trying to summarize all the exciting developments that were happening in urban settings and settings that involve autonomous driving and so forth. So even just if we were to look at interiors, there were several efforts using a variety of different synthetic 3D scenes or reconstructions of real spaces. And these simulation platforms were being used for quite a few different research problems and by different communities. You see a few examples here. Again, it's not exhaustive by any means. These are just to illustrate the point that there was quite a bit of activity. The top left, you have visual navigation for navigating robots, training for robotic grasping using large-scale simulation, doing experiments that look into grounding of natural language to objects in synthetic 3D environments, parsing natural language instructions and following those instructions to navigate within interiors, captured interiors, mapping instructions to actions on objects, and also using simulation to train systems that can perform dexterous manipulation like the OpenAI robotic hand that you see here. So all of this was quite impressive. A lot of activity that was relying on simulation as an enabling technology. My personal perspective on this is coming from being involved in the AI Habitat project, which is another simulation platform effort that emerged around 2018 to 2019. So let me give you a little bit of my personal summary of the world at the time. So Habitat was this project that attempted to look at the landscape and to try to propose a little bit of a standardized software platform, a software stack for doing experiments of this embodied AI type. And it started with looking at the variety of data sets that existed at the time that people were using to do these experiments, and also the breadth of simulation platforms that people had proposed, looking at what kinds of features were common and useful to people. And then at a level above that, looking at the kinds of tasks that people had defined using such simulations, like the examples that I was showing earlier. And for each of these levels, trying to design a flexible software platform that would allow you to load a data set of your choice for a particular set of 3D scenes, an implementation of a variety of fundamental simulation capabilities like efficient rendering of visuals, physics simulation, and so forth. And then a higher level API that allows you to define various embodied AI tasks on top of this. Tasks that involve navigation or tasks that involve some degree of natural language input and so forth. So this was the Habitat effort. It was very much motivated by this exciting amount of activity that was happening at the time. And it focused on providing fairly efficient and flexible simulation of the interior data sets. And here there's just a few example sequences of navigation within some of these data sets, within the Matterport 3D data set and the replica data set and other data sets. And at first, the overall goal was to just enable people to do navigate these visual navigation experiments at scale fairly efficiently. So that's my personal perspective, and it will give you a little bit of an idea of where I'm coming from as I continue with some of the points that I wanted to make. An interesting question to me at the time when working on this Habitat platform and also looking at all the exciting activity was, why did all of this happen at once? Within the span of just a year or two, there was so much interest and activity in this realm of embodied AI. Why is it that it was all so simultaneous in some sense? And in my opinion, an interesting way to think about it is that a lot of this activity was actually enabled by great work that happened just prior on establishing several 3D data sets that were available to the research community. Some of them were part of the simulation platform efforts. In the top left here, you see AI to Thor. Part of the AI to Thor was a simulation platform. Part of the effort was actually to construct a number of fairly high quality virtual rooms, which were used by the simulation platform. And this unlocked many interesting experiments. And at the same time, there were some very, very nice efforts to acquire real spaces. The Gibson environments was a data set of 570 some real spaces that were reconstructed. Matterport 3D was a data set of 90 residences that had fairly high quality 3D reconstructions that could be used for simulation. And the more recent data set, the replica data set, is a data set of 18 or so near photorealistic rooms that again enable one to simulate what the interior looks like from an arbitrary number of viewpoints. So all this effort that went into collecting and creating these 3D data sets, I think really helped to enable the exciting activity around establishing simulation platforms and all the various embodied AI tasks that were carried out on top of them. And of course, that didn't stop there. It's I've been talking about efforts that have happened 2 to 3 years ago. if we come back to today, if we come back to year 2020, exciting times actually continue. So there are still developments along these lines. There are a variety of simulation platform efforts. There's an example here. RL Bench is a recent effort that focuses on robotic manipulation of very interesting interactive objects. There's also the IKEA furniture assembly platform by Lee et al., which is another very interesting new simulation platform effort where one can set up tasks that involve assembling IKEA furniture. And then there's the recently released Sapien simulation platform, which again focuses on interacting with a variety of objects, fridges, cabinets, and so forth, taking objects around, putting them into other objects, and so forth. And the continuation of the Gibson effort, again focusing on interaction with the environments, having a robot that can move around and also to push objects around, pick up objects, and so forth. So there's a continuing, actually a very impressive amount of effort into establishing a variety of different simulation platforms. And here, I would like to summarize three interesting trends in the recent developments that I think will have interesting implications for people interested in research on holistic 3D vision. And let me see if I can quickly summarize these emerging trends in simulation. The first trend is more scale. So this is a simple title here, but what do I mean by this more scale? A concrete example of it is this recent paper by Eric Wiemens et al. At this year's iClear on learning near perfect navigators from billions of frames of experience. And it's impressive what kind of performance these navigation agents can achieve when trained for massive amounts of experience. But behind the scenes, what's happening here is that all these experiments are actually relying on pretty much the majority of available 3D scenes to be used as a testbed for training and evaluating these agents. So the experiments in this paper actually used both the Matterport 3D and Gibson scene datasets, combined them to create a mega dataset essentially, and carried out experiments in that setting. So really the availability of those scenes at scale is what unlocked these kinds of experiments. So in essence, this means that people are interested in using more scenes, which is kind of an obvious statement, but it's substantiated by a lot of recent work. A second trend, which is interesting, is that people are focusing more and more on settings that require interaction. And that means interaction in the sense of these robots that can navigate and interact with objects that you see here in the left, examples from the iGibson platform, a robot that can go up to a door and pull it open and so forth. And also settings that involve more finer grained interaction with objects, like the robotic arm that you see here on the right from RL Bench, playing Jenga or picking up a plate and setting it on the table and so forth. So people are becoming increasingly interested in these settings that involve some degree of interaction between the agent and the 3D environment that is being simulated. And this is a frontier for a lot of research in embodied AI. Systems that are practically useful in the real world will have to interact with the world to some extent, and so that's why partly this is a direction of great interest. And what this means is essentially that people care now about dynamic scenes. They don't just care about static representations of real world spaces. They care also about how those scenes can be interacted with. The third trend that I see emerging is that people are becoming interested in more modalities beyond the visual. And a concrete example of this is a paper presented at this year's ECCV, actually, this paper on sound spaces by Chen et al. And this is a very interesting paper that looks at embodied AI agents that navigate within interior spaces, but now the agents possess the ability to listen, to actually process audio signals. And it's kind of obvious why this is a useful ability. For example, if, say, you wanted to find your phone that was ringing, that you left somewhere, it's practically very useful if you can actually hear the ringing sound of the phone. So this is just one example, and there are other interesting examples that incorporate other non-visual modalities, such as haptic sensing and infrared vision and so forth. And generally what this means is that people are becoming increasingly interested in multimodal simulation. So these three trends, I think, lead to three challenges that are, I believe, of interest to researchers in holistic 3D vision. And I'll try to describe this in parallel to the three trends. So the first challenge, it's kind of obvious. It's in parallel to the desire for more scenes, more scale, focusing on capturing 3D scenes at scale and all the research problems that brings with it. And the scale here has a couple of different interpretations. It can have the interpretation of larger volumes, of course, having systems that are more robust, that can acquire the real world, a larger variety of spaces from the real world. But it also has the interpretation of spatial scale. Because for many of the kinds of embodied AI problems that I was describing earlier, of course, a natural setting is these interiors. So reconstructing entire buildings is of interest. And here I'm just using some prior work as example visuals to illustrate the acquisition of the spaces at a particular scale. But also of interest is acquisition at the street level. So being able to acquire urban landscapes, suburban landscapes, and to be able to set up simulation at that level. It's kind of obvious that it would be useful for autonomous vehicles and also for other practical systems that have to navigate not only within interiors, but also outside as well. And bringing that together, having structured models of entire urban landscapes, cities, is quite useful, again, for navigation purposes outdoors, and also potentially for planning how to cohesively interact with people in urban settings. So essentially what this challenge for holistic vision implies is that in order to satisfy the needs of a variety of people interested in doing simulation at all these different levels and at scale, a wide variety of environments, a little bit more attention will be needed for doing multi-scale acquisition and also acquisition of 3D environments hierarchically, starting from rooms to floors of residences, to entire buildings, to streets of buildings, to cities, and then eventually connecting these levels together. So that's one interesting direction for research challenges that I think will be of interest to people in this workshop. Another direction is kind of obvious. Again, connecting to the desire to have more interaction, to have dynamic scenes. And this is focusing on the ability to capture dynamic scenes, of course. And what does this mean? This means essentially both the ability to handle acquisition of the static parts of the environment in the presence of dynamics. So say, acquiring the static scene while people are moving about, people or other agents are moving about, or while the time of day is changing, while maybe some objects have been moved around and so forth. So acquiring the static structures in the presence of dynamics, but also acquiring that properties that are useful for the dynamics, for interacting with the scenes. And this essentially means methods that can handle the temporal axis and methods that can acquire physical properties that are then necessary to actually set up simulations of the dynamic scenes. So physical properties like the masses of objects and the coefficients of friction of different materials in order to be able to then push things around, to open doors and to close doors, and have that be simulated plausibly. So this, I think, is another challenge for holistic 3D vision systems. And the last challenge that I'll try to sketch out here is capturing for multimodality. It connects to the desire for more multimodal simulation. And I'll try to state this relative to this very exciting recent work on the structured 3D dataset by Zheng et al., which is being presented as well here at ECCV. And it's exciting. It provides a variety of different structured representations that are useful for many tasks in holistic 3D vision. But an interesting direction to extend such work is to start to consider what additional properties and structures are necessary in order to be able to have multimodal scenes, to simulate scenes multimodally. And that will have to include acquisition of non-visual properties, some of which I described earlier for the dynamics aspect, so friction, coefficients, and so forth, but also other properties that have to do, say, with acoustics, with how would sound propagate in a particular environment, or how would non-visual spectrum, say, infrared light propagate around, or what objects will emit infrared light if they're turned on. So all these properties that we typically don't consider if all we care about is just rendering the visual appearance of the interior or just reasoning about pixels in a camera image, these become very, very important if we start to consider multimodal simulation. So this, I think, will be another direction, an interesting challenge, a frontier for holistic 3D vision, incorporating acquisition of these properties, having data sets that have these properties, working on methods that can correlate these properties with visual properties, and so forth. So that's pretty much it. Here I'll try to summarize the three trends and three challenges that go along with them. So trends in simulation for embodied AI: more scale, more interaction, and more modalities beyond just the visual. And these three trends kind of imply interesting challenges for holistic 3D vision: capturing 3D scenes at scale, both spatially and in terms of diversity, capturing in the presence of dynamics and also capturing for dynamics, and capturing for multimodality, capturing multimodal properties such that we can then simulate beyond just the visual. So that's pretty much it. I'll try to end with a few takeaway messages that I hope I convinced you about. So firstly, I just want to say that there's a growing community interest both in computer vision and also other related communities like natural language processing, robotics, computer graphics, in this realm of embodied AI research. AI that involves these embodied agents that can physically act in simulation and eventually in the real world. And then that this simulation for embodied AI direction offers quite a few interesting trends that mirror, that suggest frontiers for research in holistic 3D vision, challenges around capturing scenes multimodally, capturing scenes at scale, and so forth. And I think there are big opportunities here for impact in a large number of communities, doing a better job at acquiring the real world in all its various ways. All the interesting properties of the real world from the 3D vision perspective can enable a lot of interesting research in other communities, and I think can bring broad impact. So that's pretty much it. This is the end of the talk. If you'll allow me here just a few seconds, I'll have a brief plug for the visual computing labs at Simon Fraser University, my home institution. We are a vibrant community of researchers in visual computing. And if you're at all interested in research topics related to this talk or any other research topics at all, do feel free to reach out. We're always happy to hear from interested people. Thank you so much, and goodbye.